So, hi everybody. We just stopped in the middle of the in the middle of things in media res, let's say. So I will open again my paperwork and I will go on to show you what this was all about. So here we discussed about the conditions that the characteristics that define a chaotic system, and here is an example through the linear map that is thus described: x with appendix n plus 1 equals 2x with n. So is this system, this linear map, is sensitive to the initial conditions, and because two different values of x, two slightly different values of x, can evolve diverging and thus increasing their distance, but its evolution is predictable and the variable evolve towards infinite. That is to say, after a certain and sufficiently high amount of steps, it becomes greater than what we want, so it doesn't have a chaotic behavior. Instead, this other non-linear map, which is x with n plus 1 equals 4x with 1 multiplied by 1 minus x with n, is a chaotic system because it is sensitive to initial conditions, does not have a predictable evolution, and for initial values of x between 0 and 1, it remains confined into a finite space between 0 and 1, and thus exhibits a chaotic behavior. This simple equation is called logistic map, and it describes mathematically the growth of a population through time. The fact that the value of x is limited, it indicates the fact that any population cannot grow indefinitely, since it has an amount of resources that is necessarily limited. From the point of view of the orbit of the system in the space of phases, a chaotic system often shows a dynamic that is characterized by a strange structure. But this is not to be considered as an absolute rule. For example, the second linear map presented above is not characterized by a strange structure in and in the thing that in the space of phases the orbit cannot be infinite but is cyclic, while a strange structure is always an orbit of infinite length. So a peculiar characteristics of a chaotic system, even if it is not deterministic, is the belonging to I'm sorry, I misread it. Is the apparent unpredictability of trajectories of the system, and this is due to the high sensitivity towards initial conditions. A small mistake in knowledge of the state of the system in a certain moment can provoke a mistake even greater in the prediction in the mid and long term. So a chaotic system, an autonomous chaotic system, is necessarily nonlinear, and furthermore, if time varies with continuity, the space of states can have a dimension that has to have at least three dimensions. For systems with discrete time, instead, it is sufficient just a single state variable. So here we can see the butterfly effect on the Lorentz attractor. Here you can see a representations with time that goes from 0 to 30 seconds, and here on the left you can see the Z coordinate. So this is in parametric coordinates. And here it says that the pictures, this is from Wikipedia, the pictures show two trajectories that evolved into 3D space in the same period of time. The cardinality, the coordinate, the difference between the blue segment and the yellow one is that the initial conditions has a difference of 10 elevated to the -5 in respect to the coordinate x, to the x-axis. The second graph here is the difference between the two trajectories. At the beginning, the trajectories are almost coincidental, but at the time 23, you have an abrupt divergence of the trajectories that separate for a distance that is analogous to the dimension of the trajectories. From the first image, you notice that the two trajectories terminate into radically different positions. So, going on, here we describe general notions on dynamic systems, and we'll leave this to another video. So bye for now, and don't forget to love each other, don't forget to share the knowledge, and never stop exploring. So here's my mother. Say hello. Say hello, mommy. Say hello. Here she is. And now I'm gonna stop this video and see you soon.